data and modeling with polynomials. So we've done this before with linear equations and with quadratic equations, which would both be polynomials. And now we're going to look at it beyond those powers and higher powered polynomials and how we are able to deal with that idea in that sense. So we're looking here at some vocabulary. So you can find this vocabulary in your book. You can look it up online, whatever the case may be. R squared, we've already talked about correlation. So R squared is a measure of the correlation. And remember, that value is going to be some number between 0 and 1. And the closer it is to 1, the better that it is for us. And again, when I say the better that it is, I'm saying that that regression fits our data well. Okay? So better in our case means the regression that we ran fits our data well. So we're going to go ahead and run some data, take some look. While we're doing that, remember what we've done with our data in the past is that we have used it to predict things. Our predictions fall into one of two categories, the words that you see up here, interpolation or extrapolation. So interpolation is making predictions within the data. So if the data goes from the year 1990 to the year 2000, you're only making predictions within that time period. Extrapolation is using the data to make a prediction beyond what it is, and that is less reliable because we don't know what's going to happen in the future. All right, so make notes about whatever those vocabulary words you need to make notes of, and then let's go ahead and look at the data. So here's an example of data. We're going to enter this data and look at the scatter plot, and you guys are going to record things here about the equations, the sketch, and the R squared value. And so let's start with a linear regression. So the first thing we're going to do is we're going to enter the data. So remember on your calculator, we go to Stat, we go to Edit. I'm going to go ahead and clear out what's in the list that are here. And I'm going to enter this data. So 0, 5, 10, 15, and 20. And for my y values with that, 10.1, 2.8, 8.1, 16, and 17.8. Okay, so let's look at the scatter plot. Remember how to do this. We go to second stat plot. We go into one of the plots and we turn it on. We make sure a scatter plot is chosen, that our lists are there and our marks. We quit this, and then to see it, we're going to go to Zoom and choose choice 9, which is Zoom Stat, and we can see our data. Now, you see another curve going through there. That's because in my y equals menu, as soon as this is finished, hold on a minute here, I have some equation from before. I'm going to clear that out and go back to my graph. So here is my data. Okay, you can see it's up here. It goes right here. So if we ran a linear regression on this data, so I'm going to choose choice 4. And I'm going to choose L1, L2, and I'm going to store it in Y1. We've done all of this before. That's why I'm going a little bit quickly. All right, so here is what we get for our equations. We're going to want to jot this down in our R squared value. So our equation is 0.572x plus 5.24. And our R squared value is 0.55. So if we, sorry, I'll write more decimal places, 0.5538 for our R squared value. And then go ahead and look at the graph. You can see the line. I mean, it's okay. It kind of goes with the trend of the data, but you can see with our R squared value, it's not that big. The data is not that close to the line. So let's make a note about what this looks like in our note guide. So you're going to make a sketch of that in the sketch area, so go ahead and do that. And then we want to write down the equation. And our equation, again, was y equals 0.572x plus 5.24. Go ahead and draw the sketch that you saw previously and our R squared value was 0.5538, which is not that strong. All right, so let's go back, and now let's run a quadratic regression. So I am going to go back to stat and go to calculate again. And this time I'm going to choose choice 5, which is a quadratic regression. And again, I'm going to tell the calculator I want to use what's in list 1, list 2. And this time I want to keep my linear one in there, so I'm going to store it in Y2 instead of Y1 so that I have them both in there. Press enter. So here we see our equation is going to be y equals 0.059x squared minus 0.617x plus 8.211. And the r squared is 0.7631. So I'm going to go back to my graph. So they're both in there. If you want to turn off the line, you can. So you can see the quadratic kind of fits the data. It hit this point up here. It went lower, and then it went up. And then according to the r squared value, it fits a little bit better than our linear data, and I'm going to record this information on our sheet. So this time, sketch what the quadratic looks like with the data. So you have your data points and your quadratic in your sketch, and then make a note about what our equation was. Our equation was y equals 0.059x squared minus 0.617x plus 8.21. Make a sketch of, 211. Make a sketch of the data with the quadratic running through it, and make a note that your r squared value is 0.7631. All right. Now we're going to do the same thing, but higher order polynomial, something we haven't run before, a cubic regression. So I'm going to go back to stat, over to calculate. In this choice, I'm going to choose choice 6, which is a cubic regression, and I'm going to type in the same things as before. List 1, list 2. And again, I want to keep the other equations in there for comparison, so I'm going to store this one in Y3. So let's see what we get here for our equation. We get y equals negative 0.012x cubed plus 0.433x squared minus 3.23x plus 10.081. And our r squared value is 0.9998. So let's take a look at that on the graph. All right, so make a sketch of this. Notice that the cubic, so there's our linear, there's our quadratic. Now watch the cubic. It almost gets every point, so it seems to be a pretty good fit for this data, and that also shows up in the r squared. So visually and with our r squared value, it looks a lot more like our data. So I'm going to go ahead and record this information. You can make a sketch. So our equation was y equals negative 0.012x cubed plus 0.433x squared minus 3.23x plus 10.081. And our correlation coefficient was 0.9998. Okay. So below that, there's a question on your note guide that asks you this. Which equation would you choose to model the data and why? Write a little explanation and bring it to class with you tomorrow. We're going to discuss it. In your explanation, include visually what you saw in the scatter plot as well as mathematically what you saw with r squared as why you would choose the model that you're going to choose. All right, now we're going to do an example. Here are some years, and it says what is the linear model that best fits the data. Use the model to estimate egg consumption in 1995. So we have years and we have egg consumption. So we can go ahead and enter that data into our calculator. So I'm going to go to Stat. I'm going to go to Edit. I'm going to clear out the information I had in here before because I don't need it anymore. I'm going to go ahead and enter this data. I'm just going to go ahead and enter the year number since they do work chronologically. There are other ways we could do this, like 1970 could be 0, and then 1980 could be 10. But if we want to have the same equation, we should be consistent about it. So for the notes here, I'm just going to enter year. And then in my Y values, I'm looking at egg consumption per capita. how many eggs a year we are eating. All right, so there's my data. Now I am going to go to Stat, Calc, and the first question asked for the linear model, and then we see quadratic model, and then we're going to choose what's best. So I'm going to go ahead and choose choice 4. I'm going to do a linear regression. My data is in L1 and L2, and I want to store this equation in Y1. Get my equation. So go ahead and mark this down. Our equation would be y equals negative 2x plus 4,231.5. And our r squared value is 0.7140. So that might be important in making your decision about what's best. I'm going to go to my y equals. Now, I just stored this equation in y1, but I'm going to clear out the y2 and y3 because those are from before. And I'm going to go to Zoom and choose choice 9 and have it rezoom with my new data. All right, so here's my new data about egg consumption. Here's the line. So you can see it's okay. That's probably why the correlation was 0.7140. And then it says use the model to estimate egg consumption in 1995. So I'm going to go back on my note guide and write down what I figured out. So the linear model of best fit for this data was y equals negative 2x plus 4,231.5. As a note, it had an r squared value of 0.7140, because that could be important later. For the egg consumption in 1995, I basically need to take and plug in the year 1995. I used whole year values, so that's what I'm going to go ahead and use here. So I'm going to take this and plug it in and calculate my predicted egg consumption in the year 1995. And we get 241.5 as my answer. Okay? Some other notes to make about the linear model. Pay attention to how it looks on the graph. Remember, we need the visual and the mathematical. So the r squared is important to us, but what it looked like on the graph is important to us too. Interpolation from our first data point to our last data point, we can see that maybe egg consumption is going down. But as we continued, the egg consumption is going to eventually go into the negatives. Does it make sense that, say, in the year like 2050, to have a negative value of egg consumption? It doesn't. And that's because extrapolation is kind of a gamble. You don't really know if your model is going to hold up for those places beyond that. All right, example 2 asks for a quadratic model and using that to estimate the egg consumption in 1995. So I'm going to go back to Stat and do Calculate, and this time choose choice 5 for a quadratic. And I'm going to tell the calculator that my data is in L1 and L2. And I'm going to go ahead and store this one in Y2 so I can keep my linear one if I want to compare. And so I get this equation, y equals 0.13x squared minus 518.1x plus 516,444.5. And my r squared value is 0.9554. So then in order to calculate what this is going to look like in 1995, okay, I am taking my equation. So let me write down what that was. I'm going to make a note about my r squared value because I know in a future question I need to make a decision. And I'm going to calculate predicted egg consumption from 1995. So I'm going to go ahead and do this calculation. You guys should be doing the same. Sorry, one note about something that I copied wrong here while I was doing my equation, a minus sign. The way I figured that out is in my calculation I got a ridiculously large number of eggs that we would be consuming. So I'm going to fix that. All right, so when I do that, I get 238.25. So I would either estimate that at 238 or 239 eggs, depending on how you are viewing the data per capita. So then example 3 says, which is the better model for estimating egg consumption between 1970 and 2000? So that would be interpolation. And which is better for extrapolating egg consumption beyond 2000? And again, in some cases, people would tell you extrapolation you shouldn't even do. If we were going to do it here, which model would you rely on to tell you what was happening beyond the year 2000, which is beyond what your data was telling you? Okay? So go ahead and write which one and why. Again, use the visual, use common sense, and use your R-squared values to help you, and bring this to class with you tomorrow.